Testing, testing. One, two. Yay! Good. Testing. Hey, Susan, can you hear this?
Yes.
You heard that through your. Yeah.
And I can see all the searches that you do.
Yeah, sounds good. What I'm trying to do is get the YouTube channel and GoToMeeting channel to perform simultaneously through the same microphone.
Huh. That sounds complicated.
It's more complicated than it should be.
Welcome to the webinar. You have entered as a panelist and may now speak to any other organizers or panelists on the line.
Hey, how's it going, Tara? It's Cody.
Hey, Cody, how you doing?
Doing well. How are you?
I'm doing fine. You can hear me just fine?
Yep, everything sounds good.
All right. Hey, I'm doing something a little complicated with my microphone, so can you talk to me for a minute?
Yeah,
I just want to make sure,
yeah.
make some noise or something. Tell me, how's the weather going in Half Moon?
Hold up. Yeah, the weather over here is a little gloomy. Um, it's kind of cooler than I'd like it to be. Hopefully, it heats up. It's supposed to actually heat up on this weekend, so looking forward to that. How's everything sounding so far?
You're a little, uh, I don't know, a little digital, I'd say. Like it's not crystal clear.
Hmm. Okay, and that's obviously it's different than
Yeah.
what it's been in the past.
No, I don't think so. I don't know. I'm kind of what I'm doing is I have an external mic and then a sound filter going, but I'm what I'm concerned about is it looping because I'm having it play to a recorder and play to the channel at the same time. So I don't know if when you make some music if it loops through. I'm gonna play a YouTube video. I think it'll well, I don't know if it'll do the same thing or not. Susan, can you
Okay.
go listen to it and see if it sounds like it's looping? So how many attendees we got today?
That I'm not sure. I could check real quick. Well, it looks like we already got 10, so that's looking pretty decent.
All right. Well, I'm all set up to go at the top of the hour, so whenever you're ready at the top of the hour, go ahead and just start it.
Okay, perfect. Yeah. Yeah, so we got about 2.5 minutes or so. So it looks like we got soils and causes of erosion for an hour. Does that sound right? Oh, sorry. Wrong one. That's my next series. This one is solar photovoltaic project design and development part one for 3.5 hours.
Yeah, I don't think my soil erosion presentation would be very good.
I think the attendees would be a little surprised with that one.
It'd be very limited. And, yeah.
They'd probably be a little confused.
right, well, I'm ready when you are.
Perfect. We'll take about 1 more minute. We'll stop or start at the top of the hour. And by the way, we have 21 registrants for this class.
Wow, all right.
Yes, we got a nice group.
Yeah, it's real good. We only had 9 for the off-grid class last week. I was kind of surprised at that. I thought off-grid should be getting more and more popular, but I don't know.
Yeah, weird. Is that a new seminar that you're teaching now?
Kind of. But anyway, it's the top of the hour, so I'm ready to go when you are.
Gotcha. All right. I'll start it up. I'll go over the notes as normal and then hand it over.
All right.
All right, let's do it.
The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to today's webinar, Solar Photovoltaic Project Design and Development Part 1. My name is Cody. I'll be your moderator today. This webinar will last for 3.5 hours, and we do have some notes to cover before we begin. Please be sure to be logged on to the webinar through your own individual connection so that we can accurately prove attendance in the event that you or Half Moon Education are audited. We require individual connections so that you can access the quiz at the end of the webinar. The quiz will automatically appear on your screen after I end the webinar. If you are unable to successfully submit the quiz, you can access the quiz via the thank you or follow-up email that is sent about an hour after the webinar has ended. Certificates will be issued for today's webinar. If you did not successfully submit the quiz after attending the webinar, please be sure to complete the quiz through the thank you or follow-up email. The certificates will be sent via email in PDF form, and if you need your certificates sooner, please reply back to any emails you have received regarding these seminars or call into our office. We will be taking questions throughout today's webinar. If you have any questions, you can ask them in the questions area of the GoToWebinar panel. And lastly, materials for today's webinar were sent via email. If you did not receive materials, you may access them in the handout section of the GoToWebinar panel. And with that, I'll hand it over to our speaker today, Mr. John Ross Cromer. He is a master electrician with a mechanical engineering degree from the University of Pennsylvania, a NAB CEP certified PV installer, and author of Solar Power Design and Development, An Introduction to Rooftop Solar. Take it away, JR.
All right, thanks, Cody. We're going to dive right in because we have a big program today. Hopefully we will learn solar design and make you much more comfortable talking about it with your clients when incorporating it into your projects. My background, I guess I've been working in solar for about 10 years now, a little over 10 years. Before that, I spent about 3 years in oil and gas doing control system engineering and then a little bit of contract management. I'm going to start out with just some very high-level solar knowledge. Now, I think kind of the most important thing you can keep in the back of your head is that solar is driven not just by how much electricity you produce. The desert in California gets great sunlight. The Northeast coast, not so much. But that's only half of the equation. The other half is how much electricity is worth. So, on the Northeast coast, electricity is very expensive. Even though they don't get good sunlight, solar is very popular on the Northeast coast because of how much value that on-site solar generation has. I'm based out of Mississippi, and Mississippi actually gets pretty good sunlight. What's nice about our sunlight is that it's year-round. We don't really get snow so much. And our price of electricity is pretty high, except that the buyback rate from the utility, when you outflow onto the electric grid, it's very low. It's not anywhere near retail value. It's closer to 20% of retail value rather than a full retail buyback. And so even though we get decent sunlight in Mississippi, solar production is not worth very much, being at average electricity pricing, and even worse for the buyback rate from the utility. And so what drives the solar industry more than the amount of sunlight you get is two things. One, what is just the raw cost of electricity in your area? And then two, how the utility compensates you for what you outflow onto the grid, and to some extent how they charge you for the electricity that you buy from the grid, which is more of a commercial issue, which we'll get to a little bit later on in the program. I always seem to go all the way to the end, and so I thought, well, first things first, let's do a budget update. This was a project that I actually did at the tail end of last year, and so I thought I would share my actual hard data, my hard numbers with you, so that you could see what a typical battery-less solar array could cost. What you can see in this is that the solar industry, we price by the watt, and so you see down at the bottom here a $2.50 a watt retail price. But if we go and we look at what the national average pricing is for residential installed solar in 2018, there's a very different picture. Now, I'm in Mississippi, and as I said, we don't have very good solar policy. So we also don't have much of a solar industry, and there aren't very many solar installers in this state. My competition is not necessarily other solar installers, but just raw, hard economics trying to make the systems cost effective. And so I kind of have to keep my price as low as possible, just so that the payback is something that customers are interested in purchasing. What we can see is most solar installed in the United States hovers a little over $3 per watt. Now, maybe I should report my data to Energy Sage so Mississippi can be a leader in solar installation pricing. But I'm just one installer, and there's only about 3 in this state. And so you might be on the Northeast coast, where you get a better solar policy, higher price electricity, and so even though solar could be cheaper, it doesn't have to be. And that's the opportunity here, is to kind of understand what goes on in solar design and development, so that you can lower your project cost and become a stakeholder in this industry, whether it be through project ownership or through being the design and engineering, or even the installation firm. There's still a opportunity to get into the market. At the same time, on the Northeast coast or out in California, where solar is a better value because of the price of electricity, maybe you can use higher end components, get into more of the BMW and Mercedes of solar modules rather than the Honda or the Nissan. I install more Honda and Nissans than BMWs, again, because of our policy. And so let's take a look at what goes into solar pricing. And I know this particular chart, it says 2015 and 2016, but think about what we just learned about the average pricing being around $3 a watt. And we look at this chart, and we see residential 2016 around $3 a watt. This is still pretty good data as far as how the budgets lay out. And what's happened is solar's gotten cheaper, but we've also had import tariffs kind of keeping the price of that solar panel high. And so what we can see in the dark blue is the solar module itself, hovering around 45 to 50 cents per watt, including the import tariff. We got the solar inverter being a little bit less than that, maybe around 30 cents per watt. They can be cheaper for low end, more expensive when you get into battery components. Your electrical balance of system material, and that is, you don't want to get too cheap on your electrical BOS. There's some nice things you can do that we'll be talking about in class to preserve system value, such as internal cable runs to keep the array looking nice. And sometimes the more fancy you want your system to look, it's not necessarily that you are increasing your cost exorbitantly, but you do end up spending a little bit more on your balance of system electrical components. You got your direct labor cost. That's the take-home pay of the installer, excluding things like profit and overhead, supply chain markup. So that's really what the guys out in the field are taking home in their wallets at the end of the project, not necessarily the development company or the sales rep or the project manager. Structural, that's your racking cost. So racking is around 20 cents a watt. Design, engineering, and permitting. And then the rest of this, which is pretty much half of your project cost, is what's called soft cost. And that is your supply chain markup. That's also your sales commission. That's also the 30% margin that the developer is charging to manage and do the construction financing and put it all together. And so what we can see is that, if you can get rid of soft cost, let's say you are an ambitious do-it-yourselfer with some electrical skill and you want to add solar to your own roof as a hobby, you might only pay a little bit in supply chain markup and see your cost being, below $2 a watt. You could also go through a competitive bid process and see some of these margins go down lower. And so it's always good to get multiple quotes. Why I see in the industry a lot of online sales companies. One was targeting Mississippi last year, and they were selling, way above the $4 plus a watt range. And, how they were doing that was essentially kind of misrepresenting grossly the economics of the system to the customer. It's always good to get multiple prices. It's always good to, at least on your bid list, include a local installer who might have a better, more skin in the game in terms of providing honest data, and also might be more knowledgeable of your actual local buyback rates and utility policies and things like that. What we want to do by the end of the day, or at least by the end of the program tomorrow, is allow you to do array layouts, material lists, performance estimation. So here's a sample material list, and you'll be able to generate, material lists like this by the end of class. Well, let's start at kind of what I think is a good beginning, performance estimation. How do you know how much power in your area a solar array will produce? Well, let's do some terminology. Here is a solar panel, And this particular panel is 250 watts. Now that is a little bit small compared to what is being installed today. What's being installed today is closer to on the low end 290 to 300 watts, which is what I typically install in Mississippi. On the high end, for your high efficiency panels that are the same size, just more dense, they can go all the way up to 350 watts, but they're also much more expensive. So that's more of a, when you get into markets where you have very limited real estate, like Long Island, New York, you go for the 350 watt modules. If you're in Mississippi and you got, really easy, simple rooftops, plenty of real estate, and you need to go for a lower installation price to make it cost effective, you go in on the low end. But I used 250 watts in this example because I wanted to make the math kind of easy. So we have 4 250 watt solar panels, and together this would be a 1 kilowatt solar array. And so if this 1 kilowatt solar array were exposed to sunlight for 1 hour and it was under full sun, it would produce 1 kilowatt hour. Now that sounds really good. In reality, the solar panels themselves are listed under a lab condition. And so when we say a 1 kilowatt array under full sun for 1 hour will produce 1 kilowatt hour, that is not according to what it'll actually do outside in the field, but what it would do under the laboratory condition by which that rating was derived. And of course, the amount of sunlight in the air varies greatly throughout the day. In the morning, not so much sunlight. At high noon, a lot of sunlight. In the evening, not so much sunlight. So how do we go about figuring out how much sunlight is hitting the panels, and things like temperature impact and even things like humidity can impact your solar array performance? So how do we actually get a good idea of what our solar array will produce? Well, there is a software that is put out by the Department of Energy called PV Watts. And it's a very good starting point. In fact, I even use PV Watts to go all the way into off-grid building design, but it has a very simple, almost misleadingly simple interface. And I say that because the raw data that PV Watts uses, not only is it based off actual recorded weather data in your area, but that same actual recorded weather data in your area is used by all the commercial solar softwares that you pay for. So the same data set that feeds PV Watts, which is a free, accessible online software put out by National Renewable Energy Labs, they're an offset of the Department of Energy, that same data feeds your commercial design software. It's just that the commercial design software gets you further into the design, but PV Watts is just very good for saying, well, how much is my solar array going to produce? So what I want to do now is a PV Watts example, and what I want to find is how much power, or energy rather, 1 watt of solar will produce, how many kilowatt hours per year. Or, there's thousands of watts in a solar array, so we typically multiply that by 1,000, say how much energy will 1 kilowatt of solar produce in a year, because then you have a scalar. So if you know how much power 1 kilowatt of solar will produce in a year, then if you know that ratio, you can perform kind of off-the-cuff energy estimates with your clients. How much will an 8 kilowatt solar array produce? Well, if I know what 1 kilowatt will do, I multiply that by 8, and I get 8 kilowatts worth of production. And so, like in my region, I know that a tracking array, single axis tracking, it's a very popular utility scale form factor. I know that a tracking array will do, 1.1 watt will do 1.7 kilowatt hours a year. 1 kilowatt will produce 1.7 megawatt hours a year. 1 megawatt will produce 1.7 gigawatt hours a year. And so a 8 megawatt utility scale solar array multiplied by 1.7 will produce 13.6 gigawatt hours a year. Now, what I use is I'm more in the residential rooftop space, commercial as well. And so if I know my residential rooftop array, 1 watt will produce 1.4 kilowatt hours per watt per year. If I install a 5 kilowatt array, well, how much will that produce? Well, 5 kilowatts times 1.4 is 7,000 kilowatt hours. How much will that produce a month? Well, you can divide by 12, although as we'll see, in your summer months, you get about twice the production versus the winter months. And so what this graphic is illustrating is that PV Watts is going to tie into local weather stations, generally found at military bases and airports. And it'll base its performance estimate off of the most typical month of weather data that's been recorded at that station. So the records go back, 30 years. They say, what's the most typical January? What's the most typical February? What's the most typical March? Now, weather varies more than typical. So you get a hurricane come through. Even if it doesn't take out the electric grid, you get a big cloud cover system. You get less production. You have a drought. There's no clouds in the sky. You get more production. So this is more of a year-to-year average. You can say, well, JR, you're saying 1 watt will produce 1.4 kilowatt hours, but doesn't that mean, what about how you point the array? Doesn't that vary the production? And the answer is yes. How you orient the array does vary the production, but not as much as you might think. After all, if you draw a big loop, a big circle around this house, a lasso, the same amount of sunlight's going to fall through that lasso. It's really just how it bounces off the surface of the module that determines how much that module captures. And they apply, treatments to the module surface to try and get it to capture as much sunlight as it possibly can. And so in this example, we take Austin, Texas, where the ideal tilt angle, the ideal orientation of the array that will produce the most amount of energy for a fixed in place solar module year round, well, that's due south. And then the tilt is tilted up to your line of latitude. So Austin, Texas is around a 30-degree line of latitude. And so the ideal tilt angle for Austin, Texas is 30 degrees facing due south. Now, that doesn't take into account the other side of the equation, which is how much is that electricity worth? If you have a utility policy where they're buying back every single kilowatt hour at retail price, then the ideal tilt would produce the most amount of energy. But if they are not buying back every single kilowatt hour at retail, or even if things like the price of electricity varying throughout the seasons, a higher rate in the summer versus a lower rate in the winter, or even a time of day rate structure, which might give you a higher rate in the evening and a lower rate, in the morning or even in the middle of the day, the tilt angle might vary more by what it's worth rather than how much you're producing. But back to the point, what if we take that ideal tilt angle, and instead of tilting the array up at 30 degrees, we have a shallower roof tilt. So we're not talking about like a 612 roof pitch. We're talking about maybe a 412 roof pitch or a 312 roof pitch. And so we're not tilted up at 30 degrees. We're tilted at 10 degrees. Well, it might surprise you to know that if you take a solar panel and you tilt it from 30 degrees down to 10 degrees, you only lose about 5% of your production. You know, likewise, if you take that 30-degree tilt and you tilt it up by 20 degrees, you only lose about 5% of your production. You know, what I think is particularly interesting is if you go all the way flat and face that panel straight up in the air, you're only losing, in this case, with Austin, Texas, about 9%. And of course, if the module is flat and facing straight up in the air, how it rotates east or west or whatever doesn't matter because it's just going up. The orientation of the array, not the tilt angle, but the orientation, whether it faces southeast or southwest or east or west or whatever, can start to play a larger role, although we see if we go from due south to southeast or due south to southwest, we only lose 3%. And I'm not going to worry too much about 3%. If I know 1 watt produces 1.4 kilowatt hours and I subtract 3%, you know, it's like, okay, well, it produces just under 1.4 kilowatt hours or whatever. That's close enough. You know, going all the way to due east or all the way to due west, we start to see the performance drop more substantially. You know, but even so, we're only losing about 15%. And there's an argument to say that, you know, hey, you know, here's this roof and we have one kind of small south surface, but then we have this big open west surface and this big open east surface. And so, you know, actually there's economies of scale that say, well, maybe we do a larger project and we cover the less ideal surfaces, but even though they'll produce 15% less, maybe by doing a larger project, we get more than a 15% discount on our installation pricing. And so a large project that is off ideal can be more cost effective than a small project that only faces ideal. Because of course only one of the 4 orientations of your roof surface is going to face south. Some might even argue that going all the way to a north-facing array can be justified depending on your installation price and your cost of electricity. You know, the fact of the matter is, if I'm already up on the rooftop installing, you know, a dozen solar panels, moving on to the next roof surface and installing a dozen more solar panels is not going to double my project cost. I just double my solar panel price and I double my direct labor price, and then maybe I make a little bit more money off the project, but you know, it's not doubling every single item. It's not doubling your soft cost. And so going back a few slides, you know, what we see is that, you know, as the projects get larger and we move into commercial scale and utility scale, you know, what we see is the soft cost, that light gray margin, starts to shrink and the projects get cheaper. The projects get under $2 a watt. And of course, what we also see is that if you're at a shallower tilt angle, the impacts of orientation begin to matter less. Although it seems to me that the trend in residential construction seems to be going for steeper roofs nowadays rather than shallower roofs. It's much easier to install on a shallower roof than a steep roof. Not that you can't do it. And so what we see is that in Austin, Texas, an ideal orientation will produce 1,370 kilowatt hours a year, whereas a southwest or a southeast will produce pretty much the same thing. An east-facing array or a flat array, you're losing 10 to 15%. A north-facing array, you're losing 30%. But it's not like a hard and fast rule that says the solar panels must face south. There's a strong argument to be said, well, maybe the whole roof could be covered with your solar array. So what we're going to do is we're going to get online and do a PV Watts example. When you get to the end screen of PV Watts, you will get a month-by-month printout of how much power the solar array will produce, as well as an annual total. The number one mistake you can make is just end right there, because there's a whole nother aspect of PV Watts. If you download, let's see if I can't change this around a bit. Hold on 1 second. Let me take my pointer off. But if you go and you download the hourly results, you get all the raw data behind the calculation. So if you're an engineer, you really like to get into the brass tacks of it, don't forget to download that hourly information, because that's where you get the environmental data. That's where you get how much solar insolation, how much array irradiance. So they have a couple of different terms for it, but it's measured in watts per meter square. How much energy per meter square of surface area is falling on the surface of the solar panel. And there's more information than that. There's direct irradiance, there's diffuse irradiance, and so you can determine if it's a cloudy day or a sunny day. We use this in our off-grid designs to tabulate how many days in a row of cloudy weather you get into, which impacts the size of your battery bank. And kind of another useful bit of information is how hot the panels get up on the rooftop. So I think that we need to appreciate how hot it gets on a roof. Electrical components have temperature ratings, and the wire terminations where one wire is spliced onto another tend to be the hot points of the system. And there's when you're transitioning from the rooftop into the attic, there's going to be terminations. When you're getting from the edge of the array to your home run cable, there's going to be terminations and boxes, and your cable ratings inside your house may only have a 75C or even a 60C temperature rating. Generally your solar cable is going to have a 90C temperature rating. So you don't want to just use cable that you can buy at Home Depot all willy-nilly for wiring up your outdoor roof-mounted solar array. You need to make sure that your boxes, your terminals, your cables have a high enough temperature rating. But as you can see, on a 100-degree day in Phoenix, Arizona, the surface of that solar panel can be 160 degrees. So it definitely gets hot up there, not just on the installer installing it, but on the solar panel itself. And that does impact your array performance. Now we can calculate the impact. In fact, PV Watts does calculate that. They make some assumptions. You know, what the commercial data will do is they'll use the actual solar panel that you're designing the system with to perform the calculation. PV Watts gives you a couple of values that you can switch between. But what we see on the solar panel is what's called temperature coefficients of voltage, current, and power. And so what we see is in this temperature coefficient of voltage is a percentage per degree Celsius. That's a negative sign. Then we have the temperature coefficient of current, which is a percentage per degree Celsius. That's a positive sign. So what that means is as the temperature climbs, the voltage is going to drop and the current is actually going to increase. Now, what we can also see is the temperature coefficient of voltage is a negative 0.34. The temperature coefficient of current is a positive 0.06. And so what that means is that voltage, the order of magnitude is the absolute value is an order of magnitude greater for voltage than current. Voltage is more impacted by temperature than current. And so current is going to slightly climb on hot days. Voltage is going to drop on hot days. On cold days, the opposite will happen. You know, voltage will climb on cold days. Current will slightly decrease. The laboratory rating, it's called the standard test condition. That's what all the line items on the spec sheet, the voltage of the module, the amperage of the panel, that's done at 25 degrees Celsius. And so what we can see from the previous slide, you can easily, especially in your hotter climates, get substantially above 25 degrees Celsius when it comes to the panel temperature on the rooftop. And so to say, well, what's the performance loss between the two? You know, we look at a 25 degrees Celsius rating compared to a 70 degrees Celsius rating. We say, okay, well, there's about 45 degrees Celsius difference between the two. And if our voltage coefficient is a 0.34 and there's a 45 degrees Celsius difference and it's a percentage per degree Celsius, well, you know, what we're going to do my marker up here. No. All right, I might have to get my go-to webinar marker back up here. I think it's interfering with my other one, but here we go. So we take our 0.34 and we multiply it by our 40, let's just call it 40 degrees Celsius difference between the lab condition of 25C and what we actually saw up on the rooftop of about, you know, 70C, or in this case is if it were 65C, giving us our 40 degrees Celsius difference. That's going to be about 13% loss due to heat alone. And so you take the wattage rating of your array, and on these hot summer days in Arizona, you already know that you're losing 13% from heat alone before other factors such as the friction of the electrons as they travel down the cable, called voltage drop. And so you can actually kind of figure out temperature loss. I just use PV watts because it's a lot easier. So what we'll get at the end of PV watts is the actual output of the solar array itself. And that can be useful for things like, well, okay, summer you get greater production, but you also have the temperature loss due to heat. In the winter, it's colder, so you don't have the temperature loss, but the days are shorter and the sun is not as bright, so you don't have as much energy hitting the surface of the panel. And that can help you draw the right conclusion on sizing of panels to the inverter. We're going to get into this stuff as the class progresses. Now, another thing that's kind of interesting about PV watts as it relates to standard test condition. Now, here's your standard test condition ratings. And we have it done at 1,000 watts per meter squared with a module temperature of 25 degrees C. And then this is it's called an air mass or atmosphere thickness. That's kind of the hardest one to nail down on what exactly that means. And that it relates to how far through the atmosphere the photon is traveling. And so the atmosphere thickness at high noon would be 1. And in the morning, the sunlight travels through a greater cross-section of the atmosphere, and so you get a higher atmosphere thickness. And so they kind of, but that also is going to change by humidity and stuff like that. And so they're kind of, they're not doing a high noon reading or a zero humidity reading. They're giving you, a little bit of humidity in the air on your standard test condition. But we don't always have this 1,000 watt per meter square in the air. We go back to our PV watts printout and we can see, okay, well, here in the morning, at 6 a.m., 7 a.m., 8 a.m., we see we're only getting up to, 500 watts per meter squared. And then around high noon, we get a little bit over 1,000 watts per meter squared. And so our solar array is on. This is a 1,000 watt solar array. It's kind of turning on in the summertime or in May at 7 a.m. and it's kind of staying on until, past 4 p.m. And so the array is on all day, but it's not at full power all day. It gets into this camel's hump midday. Now, PV watts kind of gives you another number that's the solar radiation in terms of kilowatt hours per meter square per day. This is a number that's also referred to in the solar industry as sun hours, which is like how many standard test condition hours per day do you get out of your solar array. And so some solar, just be aware of this, some solar texts will tell you, there's the sun hours are only 4 or 5 sun hours a day. And some solar installers take that and say, well, there's really only a 4-hour window when the solar array produces all of its electricity. And that's not really the case. It's more of an average from, the morning into the evening that gets compressed when they're talking specifically about sun hours, which is really just a mathematical tool that the industry uses to perform some mental math. So I could take my 1 kilowatt array, and if I know that in March I have 4.8 sun hours, then I know I'm producing 4.8 kilowatt hours a day. It's not something you're really ever going to use just getting into the solar industry. Some other things to talk about on this slide. One is module efficiency. The module efficiency is really an indication of how dense the solar array is. It's not talking about necessarily build quality. So you could have an efficient module made by a lower end manufacturer and an inefficient module made by a higher end manufacturer. It's not a complete story to say module efficiency is the end all in terms of quality. Although to some extent, you won't, your most efficient solar panels are generally correlated with your higher end manufacturers. You get what we see is ISC and VOC. That is your short circuit current, and that is your open circuit voltage, compared to the VMP and IMP, which is, a layman way to describe it is what your operating voltage and your operating amperage is going to be. When you do all your sizing calculations for National Electric Code, you're using the short circuit current and the open circuit voltage so that you're not exceeding, when you size based off the short circuit current, that's your current that will not be exceeded for the solar array. Same with voltage. So, you might be hand performing some calculations and get confused about, well, am I supposed to do my sizing based off what the array is actually operating at in terms of voltage, or what its maximum voltage is going to be? You use the VOC and the ISC, the short circuit current, the open circuit voltage, when performing your safety calculations. And so PV Watts is a very useful tool. It will tell you how many sunny days and cloudy days you're going to have. It'll tell you your rooftop temperature, the surface temperature of the solar panel. It'll tell you your hours of operation, so when the array is turning on and when it's turning off. And you can use that for the shade analysis to determine, how much clearing should I have for my solar array to make sure I'm getting all of my energy out of it. And you can also download the results, not just on a month-to-month basis, but an hour-by-hour basis, which is really good when you start getting into time variable rate structures, where the cost of electricity is changing by the time of day, or off-grid sizing. So working up to our PV Watts example, here I always do a 1 kilowatt solar array. Again, so we create a scalar so that we can do mental math when talking with clients. If you know how much per year 1 kilowatt of solar will produce, then you can multiply that by whatever you want when talking about system sizing, or divide by it if you're given an electrical bill of, if I'm given an electric bill, my house uses 14,000 kilowatt hours of electricity a year, and I know 1 kilowatt of solar produces 1.4 kilowatt hours, or 1 watt of solar produces 1.4 kilowatt hours a year. I do 14,000 divided by 1.4. Oh, you need a 10,000 watt or a 10 kilowatt solar array. And so in PV Watts, I recommend, as a good starting point, putting in a 1 kilowatt solar array. I would do a standard module type. Now, they have options for other module types, like a premium module type, which might have a slightly more advantageous heat degradation rate, although it does not vary that much. It's, silicon is silicon, so there's only so much you can do with it as far as heat degradation goes. The array type it'll actually let you model a roof mount versus a ground mount. Because technically that ground mount is going to be at a lower operating temperature and getting a little bit more airflow underneath. But if you actually run the math, you'll see the performance differences are negligible. It'll allow you to do a tracking array versus double axis tracking, single axis tracking. You know, of course, your tilt angle and your azimuth. And then perhaps the factor that's the fudge factor that accounts for all of your system losses is set at 14%. Now, I recommend just keeping that as is until you know what you're doing. When we talk about inverter selection, we're going to talk about module level panel electronics like microinverters and DC optimizers that allow every single solar panel on the roof operate independently of each other. And that's going to reduce some of the mismatch losses. You know, that might take that 14% number and improve it up to 11%. Actually, let's go ahead and take a look at what goes into these system losses that comprise this 14% so that you know what it is to make some minor adjustments for your area. You know, the first one is that they're going to assume there's some dust. You know, in Mississippi, we get a lot of pollen in the air. And you're not going to be getting up on the rooftop and cleaning your solar panels. You know, I might recommend doing that once every 10 years. I don't, you know, unless you live, you know, right alongside a dirt road, at which point you might want to do a ground mount instead of a roof mount. Unless you're living in Saudi Arabia in the middle of the desert, unless you're, you know, right on the coastline and you can kind of fly a drone up there and see that a bunch of seagulls have been using your solar array for target practice. You know, normally I would recommend a hands-off approach to solar cleanliness. And so PV Watts is assuming that the surface of your modules will have some dirt and dust on them. And so they're going to be modeling 2% of your system loss from soiling. They're also going to model a 3% loss from shading. Now, keep in mind, PV Watts starts with how much energy you could possibly get on your array with no shade at all. It also is not including things like if you have PV Watts is showing at 6 a.m. that your solar array is producing, you know, it's a 1,000 watt array at 6 a.m. and might be producing 6 watts of power, 0.5% of power. Well, in reality, that's not going to be enough power to turn on and start up the system. And so I would just leave, for an unshaded array, I would just leave the shading figure at 3%, because that's going to account for the very early morning and the very late evening when shadows that are way far out in the distance can come and reach over the top of your array and get that energy down to the point where your inverter doesn't turn on or turns off at night. So I'd say 3% is a good number for an unshaded array. If you're doing solar on a shaded rooftop, at that point you have to start doing like a 3D model and running, you know, simulations that are in the realm of commercial design software. We'll take a look at some of that later. Another good number to know is snow. You know, PV Watts assumes that there will be no snow on your solar array. So in Mississippi, you know, it might snow once every couple of years and melt off by the next day. I'm not going to worry about snow. In Eau Claire, Wisconsin, where Half Moon is located, you know, they get a good, foot of snow on their roof in the month of January. And so that means for your performance estimate, you may need to go out and just clear off the month of January if you know that there's going to be snow on the roof every year and your client is not going to do anything to clear the snow off themselves. And so that's one pitfall. Mismatch. Imagine your solar panels on your roof are a chain link fence. The weakest link in the chain is going to be the one that fails. Well, it's not necessarily that the solar panel fails, but there is a tolerance that the panels have. When I'm talking about when I open up a solar panel spec sheet, it'll be a spec sheet for a 290 watt panel, but also a 300 watt panel, and also a 310 watt panel, and also a 320 watt panel. And so it'll give me, within the same form factor of the panel, it'll give me 4 or 5 different wattage ratings, 4 or 5 different efficiencies, 4 or 5 different voltage and amperage characteristics. And the reason for that is that solar is made either in a sheet or a cylinder, and then the sheet is cut into individual cells, or the cylinder is sliced into individual cells, and the cells that are in the middle of your crystal are a little bit more pure than the cells that are around the edges. And so when all these individual cells then get placed onto your solar panel, what happens is there's a little bit of a tolerance built into them. So you buy a pallet of 290 watt panels, and some of them will be 290 watts, but others will deviate from that. Now, the way it shakes out in today's industry is they test the solar panels, and they even test the cells and do a little bit of cell sorting, and the higher efficiency cells comprise that 320 watt panel, and the lower efficiency cells comprise the 290 watt panel, and all the cells are the same size, so all the panels are the same size, but out of the same production run, you get a higher efficiency panel that might be sold to someone in New Jersey. Then you get a lower efficiency panel, and that might be sold to someone in Mississippi at a lower price point. Even within that, the tier goes from 290 watts up to 300 watts, and then it's labeled as a 300 watt panel. So I open up a pallet of 290 watt panels. Some of them will produce 290 watts. Now, all of them will produce, generally the tolerances today are -0 to +5. Sometimes you get a plus or minus 3%, but that's rare. So what's typical now is it's like -0 to +5. And so actually this mismatch figure in PV watts is too conservative. Most modules today, the mismatch is going to err on a production increase rather than a production decrease. Now, at the same time, if I were using module level panel electronics like microinverters or DC optimizers, which we'll talk about later, that mismatch would no longer, the weaker solar panels would no longer be dragging down the stronger solar panels. And so, that if I'm using microinverters or DC optimizers, this mismatch goes completely away, and I'm capturing 2% more energy. So instead of using a PV loss factor of 14%, I might go and use a PV watts loss factor of 12% and still feel like I'm providing a very conservative estimate. Likewise, voltage drop, that kind of depends on your particular project. If you're upsizing your cable, you might get your voltage drop down to 1% instead of 2%. I think National Electric Code, wants you to be around 3% nowadays. And so 2% is generally what solar installers will design around. Although when it comes down to brass tacks, I'm often upsizing my cable for other reasons. And so my designs tend to have less voltage drop. Connections, every time you splice a cable, every time you stick it on one end, plug it into another end, landed on a breaker, landed on a fuse, that's going to produce a little bit of resistance in the circuit. So they're taking that into account. We're going to get into light-induced degradation a little bit later. There's another kind of degradation as well that's not considered by PV Watts. So again, like maybe mismatch is being a little bit too conservative. Maybe the degradation rate is being a little bit too, progressive or liberal. Well, actually, that other type of degradation is nicknamed nameplate rating. And so what they're saying is, hey, there's a 1% loss because that 290 watt module is not 290 watts for reasons that don't have to do with mismatch, but with something else. And we're going to get to that something else in a few slides, so I'm just going to move on from it. But basically what this is saying is that out of the box, your solar panels are going to degrade by about 2.5%. So that 290 watt panel is going to test 290 watts in the lab, but when you unbox it and leave it on the roof, it's going to lose that new car smell. And it's going to see a 2.5% drop in its nameplate rating. We're going to get into that with a warranty discussion and a chemistry discussion in just a minute. On top of your year one degradation factors, you also get an age degradation factor. They lose about 0.5% a year. And so PV Watts, again, is being a little bit too liberal in the fact that it's giving you the year one production value, but year two, year three, year four is going to be declining by about 0.5%. Generally, I don't worry about that too much. I'll model the price of electricity increasing over inflation by about 0.5% a year, and that's another thing you need to watch out for. This one developer, which is no longer licensed in Mississippi, they were modeling a 7% increase in the cost of electricity year over year. Whereas in Mississippi, it's way less than that. It's like 2.5%. And so I generally won't model, anything more than inflation and my cost of electricity increasing. There's just too much variability and too many tricks that the utility can play to, even though the price of electricity may be going up, the value of your solar electricity may be flat. At the same time, I don't worry too much about the 0.5% degradation. Lastly, we get to system availability. And this is where I think PV Watts is being a little bit too conservative. They're saying that the system is going to be unavailable for 3% of the year. Well, 3% of the year, 365 days times 3%. I mean, they're saying that for 9 days a year, the solar array is going to be offline for maintenance, failure replacement. And that's just not what's typical. I mean, if you do have a maintenance event or a failure event, you may lose your production for a week while that replacement part is being bought, fixed, and installed, and then a couple of days for diagnosing it. So, 9 days might be typical when you have a maintenance event like that, but if you're having a maintenance event like that every single year, you probably picked the wrong installer. And so you sum up all these factors, and that's where I look, okay, well, the availability is a little too aggressive, but they didn't model any loss because of snow, so you take up all these numbers and you just get a very good conservative, it's better to underestimate and over-deliver than oversell and under-deliver. So this is, you just take the normal 14% degradation factor with PV watts, and that's a solid number you can go to your client with. And if you want to be a little bit more aggressive than that, I would just get rid of mismatch if you're using DC optimizers or microinverters. Maybe knock this figure down to 12%. Once you have some experience, you'll be able to look at what your systems and your designs are actually doing in your local area and calibrate PV watts a little bit more for your particular design philosophy. Now, so let's hop online real quick. Get my pointer back. We'll go to PV watts. I'll put it in the chat block. Well, there you go. So we're gonna go, and I just moved from Starkville. It's a little too stark, just like it sounds, in North Mississippi. I moved down to the coast in Biloxi. So here I am in Biloxi. PV Watts has made some changes, so I'm not sure if it's just averaging the weather data now. It used to let you select the individual weather systems, so there may be a way to get those back up. Anyway, I'm just going to go to my system information. And here I'm putting in a 1 kilowatt solar array, standard modules. The documentation will tell you the temperature coefficients that they use. The temperature coefficients are not conservative. They overstate temperature loss rather than understate. So there's a couple of areas where PV Watts is being conservative on its estimate. I'm going to go to a roof mount, keep the system loss number the same. For tilt, and click this little info button and do a sanity check on your roof pitch. So I did a lot of 512 rooftops at a 22 degree tilt angle. 1212 is 45 degree. I'll just to be a little more accurate, put a 512 roof pitch, face due south, and click go. And what I can see is, hey, I guess living on the side of the ocean, you get that ocean breeze coming in, keeping the modules a little bit cooler, the air a little bit less humid than up in North Mississippi. And so instead of producing 1.4 kilowatt hours per watt per year, we're up to 1.5 kilowatt hours per watt per year. And I can see that in January, I'm producing 105 kilowatt hours for my 1,000 watt array, whereas in July, I'm producing 132. So that's actually pretty stable. That's not, that's real stable, actually. A little bit different being on the coast. Your weather is a little bit different than being, further inland. And then here, I download my hourly info. So here's my performance data. And so for every single hour of the year, I get my direct irradiance, my diffuse irradiance, my temperature, my wind speed. It's taking the array orientation and tilt angle and taking my direct and diffuse irradiance and converting it into the amount of radiance on the panel itself. I got my cell temperature, I got my DC output, and then I get my AC output. And look, if I want to say, okay, what is the maximum value that my solar array, my 1,000 watt solar array is outputting, I can see is my maximum output is 828 watts. And so I have a 1,000 watt solar array. It's only giving me my 828 watts of output. And that means when I come to check my inverter, my inverter only needs to be 83% the size of my solar array. Or in other words, my solar array can be 20% larger than my inverter, which is the output of the system, and I won't lose anything. Because I'm in the summertime, I go and I look, okay, well, let's scroll down to say here, July. The summertime, I look at my system output. In the middle of the day, I'm getting up to 560 watts out of 1,000. The next day, 650 watts out of 1,000. The next day, 600 watts out of 1,000. The next day, 650 watts out of 1,000. If I put an 800 watt inverter on this system, I'm not getting up to my peak capacity. If you do get up to the peak capacity, the inverter is just going to shave the top off, and that's going to stay up in your array as voltage. And so in the summertime, I'm not hitting my peak capacity because of heat, because of that temperature loss we talked about. When am I hitting this 828 watts? That's going to be in April, right around now, in the springtime, when it's sunny and cool. And for that matter, in the summertime, the sun's more up, straight up in the air. So maybe at a 20-degree tilt, that's better oriented for spring. And guess what? In the springtime, I don't really need that much power because I'm not using that much power. I'm not using my heater. I'm not using my air conditioner like I am in the winter or correspondingly the summer. And so when I'm talking about choosing the relationship between my solar array and my inverter, I am very comfortable undersizing my inverter by about 20%. So if I have a 1,000 watt array, I'll have an 800 watt inverter. If I have a 10 kilowatt array, I'll have an 8 kilowatt inverter. No big deal. So I've been referring to solar panels, what you call a solar panel. The industry, National Electric Code, calls it a solar module. And that's because the term panel in National Electric Code is already reserved for your electric service panel. So a solar panel might be an electric service panel that a solar array is tied into. So what we say is you have individual cells, and the cells are combined to a module. Batteries are the same way. You have individual battery cells, and then the battery itself is called a module. And they combine to form a solar array. We call the DC circuits and solar strings. On the AC side, you call your AC circuits branch circuits. It's kind of the nickname of them. And a solar array, we call them strings. We're going to come back to that in our inverter selection later. But let's talk about solar panels, solar modules. To kind of keep in mind how large these things are, bear in mind you have someone up on the roof picking them up and walking them across the roof and setting them down. So they're about the size of what one able-bodied construction worker can pick up and handle and set back down. And manufacturers want to cheat that out more and more and more, but there's a real physical and safety consideration as well. They make them too heavy, then all of a sudden a one-man job becomes a two-man job. And so a solar panel is about a little bit wider than a human, about 3 1/3 feet wide, a little bit shorter than your typical human, about 5 1/3 feet tall. So what that's going to allow you to do is to take both hands and stick them around the side of the panel and pick it up, hoist it over your head, or kind of pick it up a few inches and hold it in front of you. Now, at the utility scale, they say, well, you're not on a roof, so we're going to be a little bit more physically demanding of you because we don't have to worry about you falling off the roof. And so at the utility scale, they make their panels a little bit taller and a little bit heavier than at the residential level. So, typically the residential level, you get your cells and they're about 6 across and about 10 down. And that's called a 60 cell module. On the utility scale, they call it a 72 cell module because literally they've added 2 more rows of cells to the panel and made them a little bit taller, slightly more cost effective. It's not that you can't use 72 cell panels on your rooftop. It's just that I don't recommend it, particularly on slanted roofs, because they're harder to handle. It might become a 2-person job. They're rated to withstand the elements. Manufacturers know that solar modules are for outdoor use, so they design them to work outside. They're rated to withstand 1-inch hail at 50 miles an hour. Solar modules are so strong that they give the installer a false impression of strength. You lay a solar panel up on its side against the side of the house while you're staging it, a gust of wind blows it over and it smacks onto the ground, you'll shatter the glass. The installer might be surprised because he's used to just throwing the solar panel in the back of the truck and driving down the road and it being just fine. When you're working on a solar panel on a rooftop, there is some give. You can lean on them. You can, what you're supposed to do is try to do 2 things. One, try and put your weight on the frame rather than on the glass. But you can kind of Spider-Man across if you have to. Not that it's a good idea, but they're what I'm trying to say is they're more robust than weak. Really the problem when you're installing is you want to make sure you're not dragging this metal edge across the glass surface. So that's what I always have to tell my crew, you guys, you got to pick the module up, and if you're sliding it, like when you're unpacking a pallet, you make sure you're sliding it across the frame and not across the glass, or you leave a scratch. The warranty is typically 25 years, although some of the higher end modules have 30-year warranties. So they're long-term, robust panels. The module efficiency is how much power hits the surface versus how much power comes out the backside. Efficiency ranges 17% on the low end, 22% on the high end. The thing about the higher end panels that are 22% efficient instead of 17% efficient is they literally can cost 2 to 3 times as much as the lower end efficiency panel. And so typically you go for a high end panel just like you're buying off the top shelf. It's going to cost you a little more. There might be reasons to go top shelf. Generally, those reasons are you're dealing with more affluent clients in more higher real estate value properties where you're space constrained. And so you're paying for the array not to take up as much space. As far as solar panel technology goes, they're pretty much all silicon. There was more discussion over what panel technology would be dominant 10 years ago than there is today. The exception being at the utility scale, you get some non-silicon solar panels. There's a big US manufacturer that makes them out of cadmium. Not something you really want to put on your roof in case your building burns down. And then there's another manufacturer that makes them out of, they call them SIGS panels, which are copper, indium, gallium, selenium. And typically, the non-silicon panels are a little bit cheaper, but they're usually less efficient, less space efficient. So they take up a little bit more space. So it's a trade-off between efficiency and, the other system costs. Some of the more experimental modules say, well, let's try and combine them together. Maybe we have a translucent thin film on top of a silicon panel, but those are still more in the experimental phase than in the common use. This is my favorite upgrade. When I'm talking about what kind of solar panel should I buy, I don't care about efficiency. I really don't care about brand name. I mean, that's not to say I'll go and use a company I've never heard of before, but solar panels are more generic. I'm much more particular about my inverter and my racking than I am about my solar panel. But the one upgrade that I always recommend to my residential customers is to get all black panels. This array, when you get an all black panel, and there's variations of all black. The low budget all black, you get these grid lines that you can still see on the panel. Although the further away you get from the array, the more they kind of vanish. you can also get high-end all-black panels that are high efficiency, and it's literally just like a sheet of black glass covering the surface. A little bit more architectural. But it just, what they say about black is it never goes out of style. And so, I'm concerned about my solar arrays looking good. The only error that this installer made in this picture is that there's a plumbing vent right here, and obviously they did the design for it to be one big row, and I got up on the rooftop and they said, uh-oh, there's a plumbing vent there, and so they stuck an additional module over here on the end. And so that's kind of a visual party foul. I don't really like that. And they say, oh well, it's on the back of the house, so you can't see it. Well, the thing is, if I'm standing over here, the further away I get from the rooftop, I might be able to see up on that roof. Maybe not if I'm standing down right on the edge, but if I go out and turn around, I can see it. And we're going to talk about how you can fix that in a minute. It's no big deal. You just have to replumb that vent underneath the array and out the top. But, I do like the look of one big rectangular black surface as opposed to the silver frame with a white back sheet. This has a black frame and a black back sheet, and that eliminates all these little white spots that would otherwise show up on the array. Now, there's exceptions to that. If you have a silver metal rooftop, the silver frame solar panels can look quite nice. But for the most part, I'm telling my customers, consider going with an all black panel because it looks better. There are solar shingles on the market, but I tend to deal with cost-effective solar, and these solar shingles are expensive and ill-supported in terms of, it seems like every manufacturer who makes them stops making them after a few years and then kind of get passed around from manufacturer A to manufacturer B. What I'm more interested in is how to take a rooftop and build the roof out of solar panels rather than to use solar shingles for that reason. And, there's a lot of solar installers will grumble about Tesla solar shingles because they're just not available. So it's like, well, I could be selling more installs, but customers want to wait on solar shingles. And, I'm telling you, solar shingles have been able to be bought for the last 10 years on the market, and inevitably they're too expensive and the manufacturer goes out of business and stops making them. And so it's just not, and, I don't think that the solar shingle aesthetic looks any better than having an all black array hovering right atop the roof. There are frameless solar panels that do not have this frame that goes around them, which are kind of interesting. That frame is pretty useful because it gives you a support edge. So when you're landing the module on the roof, when you're placing it, when you're lifting it, that frame really helps give the installer something to hold on to. The frameless panels shatter real easy. But you might find a reason why you need them. I mean, you can get a frameless solar array, and then there's no conductive edges. You know, the ones that I've seen have been intended for purposes that have never really made it to market. So we were looking at frameless panels for a utility scale project back in 2014, and the idea was that they could just be glued directly to the racking system, and not only do you save a couple pennies not having the frame, but also improve your installation time. The frameless solar panels really got set back by not the Trump era import tariffs, but the Obama era import tariffs. And so I've only seen them really be installed in like Australia rather than in the US. Architects probably like this. These are called bifacial solar panels. Just like the all black panels took a what was a white plastic backing and made it a black plastic backing. The bifacial solar panels have a glass backing, and that allows you to see through the panel. Now, I think it has architectural purposes, where you can make a stunning custom design for a covered walkway. Kind of better connects the public to the solar panel. But they're not made, they're more available than solar shingles and frameless solar panels, less available than all black panels. They're kind of being considered more on utility scale projects simply to improve the density of the project, because they can collect sunlight from underneath the array as well as on top. However, that's not a great argument. You can use PV Watts to explain why. You know, here we have is a beam irradiance and diffuse irradiance. And so beam irradiance is a sunny day, and diffuse irradiance is there's clouds in the sky. So here on January 1st, it's really diffuse irradiance. We have zero direct sunlight and just indirect sunlight at high noon on January 1st. And then on January 2nd, you know, kind of the same thing. January 3rd, same thing. And here's January 4th. The weather system is blown through. And so what we see is that on this January 4th, we got 964 watts of direct and 80 watts of diffuse. And our solar panel's doing 728 watts. And then on January 1st, we have no direct, kind of all diffuse, and we got 80 watts. So 728 versus 80. You know, so let's assume that the underside of the panel is all diffuse light. And so what we're saying is maybe the bifacial panels will boost the performance of the array by about 10%, and they cost more. So it's, well, you know, why, if you're trying to be cost effective, you don't really go for bifacial panels. You know, there's some experimentation going on, pilot projects, studies, utility scale, yada yada, but the conventional wisdom is that the bifacial is not cost effective at this time. I look at bifacial panels more for architectural reasons, you know, being incorporated into the building in beautiful ways, not necessarily in cost effective ways. And at that point, it gets a little hard to find bifacial panels, because most of them are like this, where the cells are really closely spaced together. Whereas, I think that the ones that are the cells are spaced further apart are prettier and just to be more logical because you want to let the sunlight through. But the further apart you space the cells, the more you're buying a sheet of glass and not buying a solar panel, and so it becomes even less cost effective. And so there's only a few manufacturers who are really making kind of architectural grade bifacial solar panels. And even with those, you have to be very careful because you don't want the underlying structure to block the cells. So you have to be very detail oriented if you want to do a bifacial solar facade. So where do you go to buy solar panels? Well, probably the best advice I have is just to go to online wholesalers. And then the advice I have is to scroll down to their website. They may say, oh, have dealer pricing. Well, if you're not already a solar installer, they might not be so happy to give you dealer pricing, installer pricing. So the way around that is to sign up for the newsletter. Go and find online distributors, put your email address in the newsletter, because they'll email out pricing that is cheaper than what they'll list online. So you want to do a solar project for yourself, you want to buy a pallet of solar panels, instead of just pricing out online, work the supply chain, put your email address into distributor websites, and that's where you get module pricing that is, if you put enough time in, you'll be able to buy the solar panels at the same price that I do. We're going to take a break in just a minute. What I kind of want to finish this up on is, how does a solar panel work? It's kind of confusing because it just kind of sits on the roof and generates electricity. Well, to start out with, a solar panel is a semiconductor. And semiconductors conduct electricity under certain conditions and do not conduct electricity under other conditions. So what I think about as silicon as a photovoltaic semiconductor is, what that means is that when sunlight hits this crystalline structure, these are electrons here. They're in this kind of rigid crystal. But when sunlight hits that crystal, it's like a racked billiard table being struck with the cue ball, where the cue ball is the photon from your sunlight and causes the electrons to break loose out of that crystal and start bouncing around the cell, or start bouncing around the table. And so at that point, it becomes an exercise of, well, how do we get all the electrons that are careening around the cell to go in the direction we want them to? And so they put conductive pathways into the cell, and then it becomes a trick to get all the electrons to flow into these conductive pathways. And basically, the analogy I've come up with is, take that pool table and pick one of the ends up, and all the balls fall into the side and go into the hole. And so the way that they pick the solar cell up and get all the electrons to fall into the holes is they dope it in two dissimilar elements and create a disparity between the top of the cell and the bottom of the cell. So you get these electrons bouncing through the cell, but they have a tendency to be sucked up to the top of the cell and be repelled from the bottom, kind of like a slanted pool table. And so all the electrons stack up on the top side of the cell. There's no electrons, well, there's some, but not as many on the bottom side of the cell. And that creates a voltage potential. Just like you have a battery with a positive and negative side, your cell, once that cue ball breaks the rack, and keep in mind you're playing on a slanted table, you now have a positive and negative side to the cell, just like a battery, except it's only on when those cue balls are hitting the surface of the cell and energizing the array. And so when you have sun, you get a big positive and a big negative. You get voltage. A little bit of sun, a little bit of voltage. No sun, no voltage. And at that point, it's just a matter of connecting the positive end and the negative end to a load, and the electrons will flow through it. In this case, the load is your house, or more specifically, the load is the inverter that takes that DC circuit and converts those moving electrons to AC electricity. Now, likewise, you have all the electrons at the top of the cell. That creates a positive side and a negative side. The electrons, they want to go back into the bottom of the cell, and so they feed it back through that home run circuit. That negative circuit gets the electrons back up in there. Now, when we were talking earlier about year one degradation, what happens is sometimes the electrons leap out of the cell and they don't come all the way back. And they will leak out of the inverter ground. And so in old inverters, you would take the negative side and you would ground it. Nowadays, we have floating inverters where neither the negative nor the positive are grounded. And that reduces this what's called PID degradation. Now, PID degradation, the electrons can also leak out the frame. So a frameless module has less degradation than a framed module, although it's not worth losing the frame. The frame is very useful. You know, manufacturers have started to space the cells a little bit further away from that frame. And they have less PID degradation. It's like when you hit the billiard ball and the ball falls off the table. That's like PID degradation. And so there's build quality issues and system design issues that have been explored to reduce the PID degradation. It occurs in hotter, more humid climates. So it's a particular concern on commercial flat roofs in the south where you get a lot of rain water just pooling right underneath the array. The other kind of degradation is called light-induced degradation, and that is like the felt surface of a worn pool table. And so the billiard balls careening around the table eventually etch little gutters into the felt. So the electrons will etch little gutters into the silicon. And when they're careening around the cell, they'll fall into those gutters and lose a little bit of momentum. And that's why a brand new solar array is going to have a little bit more punch than an aging one, because those gutters have not been etched into the cell yet. It's a perfect cell. It still has the new car smell. Eventually, these pathways get etched into the cell, and the electrons lose a little bit of their momentum when they're hit by that photon. And so in general, you're going to see in the first year a step down in array performance that's warranted under most circumstances to be no more than 3%. 5%. And then from that point on, you have about a 0.5% degradation a year. That 0.5% degradation is just from weather, humidity, water getting into the seal of the solar panel and then being vaporized and leaving little blotches that make the electrons not flow as well. We're going to talk about warranties in a little bit. And so now we're getting into a real advanced issue that solar installers don't quite understand, which are called snail trails. You know, they kind of look like little slug lines, like a slug is just crawled across your solar array. But what these are breaches in the cell where electrons have started to kind of short circuit within the cell themselves, and the cell structure starts to kind of rip apart. And so these snail trails, to some extent, are inevitable. To another extent, they don't matter so much because the electrons can still make it to the pathways unless they get so out of control that the electrons get trapped, and that ultimately leads to failure, although it's a very slow process, and in almost all cases, the snail trails don't block the pathway enough to result in module failure. So this is something that will just naturally occur on solar panels, and you know, 99 times out of 100, even when there is a solar panel failure in the field, it's not a result of these snail trails. But yeah, this is a thin film snail trail, which is a little bit more dramatic than a traditional silicon snail trail. Whereas the solar panel on the right got hit with a tree branch in a heavy storm, like a battering ram. I'm going to come back to how that plays into warranties in just a couple slides, then we'll take a break. Generally, you know, there might be one or two systems where you have to do it this way, but you generally don't want your solar panels to be flat. You want to give them at least a 10-degree tilt. You know, I even think more than that, because what happens is your rainwater will clean the solar panel. So rain hits the solar panel and it dribbles down the array and cleans it, but that effect is greater at steeper angles rather than shallow angles. And what happens at shallow angles is the grime gets kind of caught in the lip of the solar panel. And so on a perfectly flat array, you're going to get lots of dust and accumulation from rainwater evaporating and staying behind on the solar panel. And even at a slightly shallow tilt, it's going to be worse than a steeper tilt. So, you know, on a flat roof, you still don't leave your modules perfectly flat. You want to give them at least a 10-degree tilt. I'm much more comfortable with 15 degrees than 10, because 10 is still pretty shallow. And so now we see a couple of things on our spec sheets. We see snow load, wind load, hail impact. You know, the module frame is available in different thicknesses, which can impact how much load it can take. So you can get a stronger module rated for, you know, hurricane winds. We see the positive tolerance, and we understand that comes from manufacturing. We see a maximum power decline of 0.7% a year. We expect it to be around 0.5%. And you get a lot of things on spec sheets. We've talked about the differences in size between 60 cell and 72 cell modules, the weight of the panel. You know, even things like the length of the cable coming out the back of the junction box, I find useful in my designs. Now, almost uniformly, these cables are going to be long enough so that the modules can be wired in either landscape or portrait. But, and this is more of an advanced installer issue, managing these cables gets messy. And so every installer has their favorite cable management techniques to do with these things. And so sometimes they're longer and you can do fancier things with your cable management than when they're shorter. Such as on a 72 cell panel, the panel itself is a little longer, so to be mountable in landscape, the cables themselves are a little longer, and that gives you just a little bit more length out of them to do some cable management. So here's a warranty. Here's a 10-year product warranty and a 25-year performance warranty. And that's pretty common of your mid-range solar panels. On your high-end panels, you'll often get a 25-year product warranty and a 25-year performance warranty. Well, what's the difference? You know, what it really means is a 10-year warranty is on the build quality of the panel itself. The performance warranty is more like if the performance starts to drop down below this and there's nothing wrong with the build quality, then that triggers a different replacement process. And so we see that there's a year one warranty for 97%. Well, that's because we know to expect about a 3% degradation because of the year one light and potential degradations. And then it declines to 0.7% to get you to 80% to year two or year 25. Well, we're not quite where I wanted to be yet, but it's time for a break. So it's about 8 till. Now, why don't we take a 10-minute break? We'll pick back up a little bit after 1, probably around 1:02 Central Time, 2:02 Eastern Time. So let's take a 10-minute break, and we'll pick back up shortly after the top of the hour. We're going to pick back up in about a minute or so. Okay, so looking at some module spec sheets, continuing our discussion. I find this to be really useful. How many modules are in a pallet? When I do designs, I try and force my customer into not getting an array that perfectly fits their rooftop, but instead having an aesthetically pleasing array that uses however many modules come in a pallet. And so that's not all installers do this. This is again something I do in Mississippi to cut cost. And say, okay, well, you get a 1 pallet option or a 2 pallet option or a 3 pallet option. And that might be a $25,000 project, a $30,000 project, or a $35,000 project. It might not exactly divide out that way, but it's more cost effective to buy by the pallet. I can go to a solar liquidator and buy by the pallet, but not by the individual piece. I can go to a mainstream distributor, and sometimes I can buy by the piece rather than by the pallet, but it costs more. It costs about 50% more. So, if you're pricing out panels and you're not finding them in the 40 to 50 cent per watt range, instead you're getting in the 60 to 70 cent per watt range, it might be because you're not buying by the pallet. It just makes everything cheaper. Shipping's easier. Just remember there's the product warranty and then there's the performance warranty. And so, that's the one thing about the performance warranty is like, okay, well, if the performance is dropping off within the 25-year time frame, then they may replace the module, or they may just cut you a check for the difference. But then other workmanship issues like the frame actually coming apart, they don't have as much control over where you actually site and land the project. So, generally they'll give you the standard is a 10-year workmanship warranty. And then from that point on, from year 11 on, the only thing that's going to trigger your warranty has to do with degradation of the cells themselves. And then commonly the warranty is 90% for the first 10 years and then 80% for the next 25. Some manufacturers will give you more of a year-over-year warranty rather than a stair-step warranty. And then actual performance is, these warranties from the module manufacturers are still pretty conservative compared to where the actual performance should be. They're giving themselves a lot of wiggle room. Probably the most important one is that year 1 warranty of 3% loss and no more than that. When a solar panel fails, what is most common is that some little soldered connection from one cell to the next pops. And what that's going to do is it's going to put a blockage in the circuit, and your solar panels have bypass circuits so that if part of the panel becomes shaded, the rest of the panel remains on. And that can not necessarily be a huge benefit because, just like one cell failing in the panel having impacts on the rest of the panel. One panel failing in the circuit can have impacts on the other panels in the circuit. And so, one part of the module being shaded will take the whole circuit down by, 1/3. And generally, shading is going to occur on the whole panel and not just one little part of it. But I guess what I'm trying to say by this is if you do have a little solder point pop and it takes out, 1/3 of the panels, well, that's going to trigger your warranty regardless of if it's a stair-step warranty or a year-over-year warranty. And so whether it's a 90% for 10 years and then 80% through year 25, or 97% year 1, 96% year 2, 95% year 3, either way, you're going to be covered if a solar panel arrives on site defective, because it's not just a 0.5% that's going to be defective. It's going to be 1/3 of the panel or so. The panel's producing 2/3 the voltage of what it should be. That's going to be covered under your warranty, whether it's the most aggressive warranty or the most conservative warranty. We got an audience question. So is the performance affected by workers stepping on the panels during installation? The answer is yes. That's the danger of the installer getting too comfortable with a solar panel, is these failures can occur kind of at the microscopic level. So you could have a solder point pop and you really can't identify it with the naked eye. You could use a thermal imaging scanner to see a hot spot on the panel that would reflect open circuit voltage, which would reflect a popped soldered connection. But you wouldn't be able to just look at the panel and see, oh, there's a wire that's not connected in there. And so the problem is, if your installers are too rough on the panels during installation, what they'll be able to see is that there's a loss of 1/3 of the voltage that isn't there, that should be there, but they won't be able to see it for themselves with their naked eye. And so, on ground mounts, you can get the ground mount built, and then your worker might be leaning or sitting on the solar panel and think, oh, there's nothing wrong, because the panel itself is strong enough. The glass itself, the frame, whatever, is strong enough to not shatter the glass or shatter the panel, but there could be a crack, in the cell. And sometimes the cracks in the cells don't matter, like we saw with the snail trails earlier, and the panel will keep working. Other times it'll result in, the connection being completely destroyed, and that results typically in 1/3 of the voltage dropping out of the panel. So, just because you can put weight on the solar panel itself, you should always try and put the weight on the actual frame and not on the surface of the glass. And even when you're putting weight on the frame, you want to avoid that, except, like I had one project where the roof was so steep and tall that we were having to build the whole array hanging off of a big forklift. And so we're like 40 feet up in the air, hanging off of a platform, putting these modules on the rooftop. And to get the clips installed, we were having to put little temporary toe boards onto the standing seams and then step over them and really reach our arms up to get to the top clip. And for that, putting a hand on the module frame to just get up to where you need is fine, but actually like stepping on the module would be catastrophic, even if it doesn't shatter the glass. what's more likely to happen is that the installers on the ground get a little too lazy handling the panels. So you lean them up against a wall and a big gust of wind comes over and blows them over and they smack onto the ground and shatters the glass. Or you're unpacking them out of the box and then putting them onto a lift to lift them up onto the roof, and you jerk the lift and the panels bounce up and down, and you know how if they're loosely stacked, then I've seen a bolt get underneath a panel frame and then the panel frame get jerked up and down and it pushed down onto the panel and shatter the glass. Usually it's going to be something like that rather than putting weight on the surface itself. But it is somewhat common, and this is another reason why I like ordering by the pallet. So when you order by the pallet, they'll come in a box of some sort. If you order by the piece, they might just come outside of a box, but stacked and shrink wrapped, and then the shipper may put additional boxes on top of the panel surface itself, and they get damaged during shipping that way. So, you do want to keep weight off of the surface of the panel. There we go. Here's a slide to illustrate that point. So that's a timely question. You read the module installation spec sheets, and they'll give you force load ratings for the panels, which can be impacted by your kind of racking structure. So you may be able to increase the weight of the array using the same panel, but adding an additional support rail underneath it. Or certain racking types may not have this support rail. They may only be securing, the edges of the frame, and that might result in a weaker system than using the rail itself. The position of the rail, whether it go along the bottom edge of the frame or a little bit into the frame, can impact the force of the array as well. And not all manufacturers will let you be so creative with the locations of your rail as well. That'll come into play a little bit more when we get into our racking discussion. One kind of advanced racking is called a shared rail racking, where normally the rail, you're going to have 2 rails per module, and they're going to be kind of, about 1 foot in on each side. A shared rail system, you get rid of one of the rails, so that might mean fewer attachment points onto the rooftop, and that also means you save the cost of the rail, although the rail is aluminum and it's not that expensive. Where I look at shared rails, I think they're kind of neat in the sense that if you get your racking selection right with your shared rail system, if it wasn't going across the roof, which they're doing here because it's a standing seam, but if you have your shared rails going long ways rather than across the short end of it, you put rails here, what happens, that I think is really neat, is that normally this is a little air gap. And so rainwater can fall into that gap and get underneath the array. But if you use a shared rail system, at least for this gap right here, you can collect the water inside the rail and kind of gutter it down to the bottom of the rooftop. And then with the use of flashing tape, you can make a completely watertight array surface, which is how on that bifacial picture where you see the solar panels were the actual roof itself. I really don't know any installers who are doing this. I'm waiting for my first client who will let me do it with their garage rather than their house. But, a shared rail system can be used to make the actual roof out of solar panels rather than putting the solar panels on top of the roof. They are harder to install. You have to be very, very precise for them to line up correctly. Another kind of unconventional racking system is a railless racking system, where you just put supports down onto the roof rather than the rail itself. And most installers are not fans of the railless system. You have to be more precise. It's much more difficult to get square. Solar panels are big and flexible rectangles. So and the rooftops are wavy, so they're very hard to square to begin with. And that rail is helpful because if you get the rail square, then the panels will go on square. But where I use railless systems is I just did one on a standing seam metal rooftop, because it's better structurally for loading, where you don't get load being transferred across the entire array surface, and so you reduce the load on the individual attachment points. Railless racking really does not save you any money. It's more of something that you should do when your rooftop is unconventional rather than as a standard design practice. So let's talk about racking design. Now, at a very high level, solar design is how many rectangles can you fit into the larger polygon. Not too hard to figure out, particularly for an engineer. There is some shade analysis, although many rooftops are not shaded. I generally do shade analysis with 3D modeling using design software. It's not always available, but let me see if I can pull up a picture here. Like, I recently ran into a building owner at a baseball game, and without even stepping foot on his building, I was able to pull up his address, and my solar design software, which had, just like how Google Earth does its 3D buildings, the solar design software and this is hard in rural areas. When I was up in North Mississippi, they didn't really have this data available, but down in Biloxi, they do. They have the elevation data of buildings and trees and stuff, so I can just, just from the comfort of my desk, do a on-site evaluation or do a site evaluation with regard to shade analysis. The analog way to do it is to get a device. This is called a solar pathfinder. And what it is, it's a chart and a reflective dome. And the x-axis has hours of the day, and the y-axis has months of the year. And where these shadows fall onto the chart will tell you what hours of the day and what months of the year you get shadows exactly where you're standing. And so what we can see is this in June and July, this tree, the solar array, might normally come on at 7 a.m. Although with spring forward, that might actually be closer to 8 a.m. And then in December, the solar array may not be turning on till 9 anyway. So this house is not as big of a deal breaker as it seems. You know, generally what you're trying to go for is at least, you know, from 9 to 3 is the best kind of solar window, but in reality it's shorter in the wintertime and wider in the summer. So maybe a better one would be, you know, from 9 to 3 in the winter, and then from, you know, 8 to 4 in the summer. So this is a fairly unshaded spot, but once the sun gets into those branches there, it'll turn off the array. You know, even though the tree will lose its leaves, the branches can still diffuse the sunlight. You can also use good old-fashioned trigonometry . So I have a little Google Maps trick. You know, a few things. One is Microsoft has a map software called Bing. It's their search engine, and they'll often have more clearly defined pictures than what Google Maps or Google Earth will have. It's always useful just to tell the client to take a few steps away from their house and turn around and take a picture of the roof line to get a, you know, good on-site photograph to tell you what's going on. And then if I'm looking at Google Earth and I see a tree around and I want to know what the height of the tree is, and I don't have software that has LiDAR data in it, you can use good old-fashioned trigonometry to start figuring things out, like building height, the height of the tree. You know, so you can find online charts that are called sun angle azimuth charts. The U.S. Naval Office puts out a really good one. So here we are on Google Earth. We put in our address, and if I want to find out what the height of this tree is, well, I can use the Google Earth ruler tool to measure the length of this shadow, which Google Earth is telling me is an 80-foot shadow. The Google Earth ruler tool will also tell me the heading of the shadow, or the azimuth of the shadow. So it's going at 160 degrees, with 180 degrees being due south. And then Google Earth will also tell me, I can't get my mouse close enough to it, but Google Earth will also tell me, I got it circled in red down there, the date the image was taken. So this shadow of this tree was taken on November 24th, 2012, when the sun was at 160 degrees and the shadow was measured to be 80 feet long. And so here I'm going, you can just Google Navy sun angle azimuth chart. But here we are using the Navy sun angle azimuth chart, and I'm going in and I'm putting the date the picture was taken. I guess it doesn't match up with the example, but I would put in, that was November 24th, 2012 in Philadelphia, Pennsylvania. And remember, the bearing of the shadow was at 160 degrees. And so what the altitude and azimuth of the sun angle chart will tell me is, hey, when the sun was at 160 degrees bearing, it'll tell me that it was 27 degrees up in the sky. And so even though Google Earth won't tell me what time of day the photo was taken, the sun angle azimuth chart will, because I know the bearing of the shadow, and now I know the elevation of the sun. And so if I know the elevation of the sun and the length of the shadow, I can use trigonometry to calculate the height of the tree. And so just by using, I can use the same thing to get the shadow of the house, to get the height of the house. That's one mistake. You don't want to get the height of the tree and forget to subtract the height of the house. But, even so, if you don't have access to fancy solar design software, you can kind of get an idea of what your tree heights are before you even get out to the job site. And at that point, you can use the same sun angle azimuth chart and PV watts to say, well, what time of day is PV watts telling me my solar array should be turning on? Where is the sun at that time? And where is the tree height? And just use good old-fashioned trigonometry to do your shade analysis. Although if there's lots of trees around, at that point, building a 3D model or actually going to site with a tool is more accurate. Then again, accuracy is a relative term because trees grow. So you might not have to be as accurate in your shade analysis. What you need to be is conservative in your shade analysis, because the trees will grow over time. And so your commercial solar design software such as Aurora and Helioscope have this LiDAR data built into them. You may be able to do this in SketchUp, although I haven't really tried. And if it's just for your own instances, Aurora Solar software, they make you pay for it, but their competitor, Helioscope, gives you a free trial. And last I checked, they didn't require you to put in your credit card or debit card information to do the free trial. It's just go to their website, log in and register, and use it for 30 days and try it out. So more than enough time in the free trial of many solar design softwares to do one model for your own, personal house. Wind speed is greater at the corners and the edges of the roof. Rather than in the middle of the roof. And so certain fire codes are going to require you to stay off the edges of the roof. And I think it's getting kind of silly because there's a lot of attention in the fire code and current iterations of National Electric Code and how to de-energize the solar array. And there's ways around, even in fire code, around having rooftop clearance. I mean, it's obvious that there's certain rooftops that firemen during a fire are not going to get on top of, and there's other house and attic ventilation systems that you can put in to clear smoke out of a house. But the bare bones default basic way when a house is on fire to get smoke out of the house so that the firemen can rescue anyone inside, because otherwise they can't see anything. The bare bones basic way is that they get up on top of the roof and cut a hole in it to get the smoke out of the building. And so if there's a solar array covering the roof, the concern is they can't do that. And so that's been incorporated into residential code to say you have to stay 3 feet off the sides and 3 feet off the top of the roof with your solar array. Now, to some extent, that's all right. You know, if your roof is overhanging the side of the house by 3 feet, you don't. That's going to be a weaker area to penetrate anyway. And so why not just leave it for the firemen so that they can climb up and get on top and scamper up the roof and cut a hole in the roof. And then it's 3 feet on both sides because they need 2 ways to access the same roof plane. They don't know what's on the other side of the roof. And so they need to be able to scamper up one side, run across, and then come back down a different way. There's a little bit more nuance than that. On a hip roof rather than a gable roof, you can go all the way to one side, because on a hip, gable roof, you have a hard edge. On a hip roof, it's kind of like the inverse of this corner. You have a 45-degree step to the other side rather than a hard step off the roof or over to the other side of the plane. So the standard design that won't get you in any trouble with any inspector is to say stay 3 feet off the sides and 3 feet off the top. And to be perfectly honest, having that extra space on the sides is something you want. You don't really want your solar array to be inaccessible in case there is a maintenance task you have to perform when you're up there. Now, hopefully there's not going to be too much maintenance you're going to have to do up there, but, if there's trees around your house and you get squirrels up there, yes, there are squirrel guards that we'll show you in a little bit, but at the same time, you can't plan around everything, and keeping some space up on that rooftop to walk around and service the array can be useful. For one thing, code is really encouraging. It's not hard and fast, but code is really encouraging the use of putting little electronic boxes behind every solar panel on the rooftop. And while that can help with de-energizing the array during a fire, it also puts a failure point on the roof that during normal operation fails and needs to be serviced. And so being able to get up on the roof and being able to service that one solar panel is not required, but useful. Otherwise, you would just start at the bottom, remove that panel, and then work your way up. Commercial buildings have these offset requirements too. And that makes a lot more sense as well, because there's work to be done up on a flat commercial rooftop. There's air conditioner units that need to be serviced, which you can't box in. So there are 4-foot pathway requirements to get to your air conditioning units. every 150 feet, you need a walkway, and there's certain walkway requirements. The standard is 8 feet, but it can be 4 feet as long as you're putting little cutouts for the firemen every 20 feet. You have to be 6 feet from the edges rather than 3 feet from the edges, because you're presumably you're walking around on this flat roof. You don't want to trip and fall over the edge because you're walking 3 feet from the edge. On top of that, these having a walkway every 150 feet, a lot of it is, these are safety codes. They're for your own good. And you're like, well, is that a little excessive to have a 8-foot walkway every 150 feet? Well, there's actually been a few solar fires that have burned down some commercial buildings. Big one was the Dietz-Watson fire in New Jersey that happened a few years ago. A more notable one was called the Bakersfield fire. I think that was like 10 years ago. And these fires occurred for a few reasons. What most solar installers know is that you have a combiner box where all the circuits kind of come into before going down to the inverter. And these inverters, the old style, had a ground fault circuit in them that was grounded to negative. And what would happen, and I'm not going to get into the details of it, but under a very weird circumstance, you could have one circuit on the rooftop ground faulting to ground and raising the voltage of this ground and not causing the ground fault detection system to work. And then all of a sudden you get all of the circuits of the array feeding into that ground fault, and it starts a fire on the roof and burns the building down. And so most solar installers say, well, yeah, but now they've kind of reworked this ground fault detection so that the inverters are no longer negatively grounded and instead are floating, and they've redone the ground fault detection to avoid that. And what that discussion completely ignored was how the ground fault up on the roof, up on that combiner box, began in the first place. Like, we know why it continued, because of this blind spot in old school commercial inverters, but what caused it to begin with? Well, what it was is rooftops are very hot, and it is common to use, metal conduit to run your cables through, and you have copper cable inside more like aluminum conduit, and it's very hot, and so the cables inside the conduit would expand at a different rate than the EMT conduit itself. And so when this EMT conduit would land on the combiner box, if you don't allow for thermal expansion, which is generally at 120 feet or greater, the conduit would pull out of the box, leave a rough edge that would bite into the conductor inside it, wearing away at the jacket of the cable and causing a ground fault. And so because these installers were not appreciating the temperature extremes on the rooftop and what it might mean in terms of thermal expansion when you have copper inside of a non-copper, very long conduit run with no expansion fitting, that combined with this fire to burn down the warehouse. And so these walkways are not just for access, but also to ensure that you have broken up your metal so that thermal expansion doesn't rip your home run circuits apart. Now, this was what we did for Half Moon. You know, they're a commercial building, but it's a slanted roof, so that's a residential type roof. And so we're staying 3 feet off the sides and 3 feet off the edges. If we were using commercial clearance requirements, we would have done 6 feet off the sides and then stayed at least 4 feet around the skylights. And we fit the array on the roof like so. And then after this point, we went and said, well, you know, what we're going to do here is we have a little bit of space left over. Let's shift the whole array over this much and kind of center this panel, you know, right above their doorway to make it look a little more square from the ground. Which any general contractor should be able to do, is figure out the starting point. On particularly long or difficult roofs, some installers will start in the middle and work outwards, rather than what's more traditional is just to start on one side and work your way down in order to preserve that kind of square-like appearance. Now, one of the problems we ran into with this design is even though you stay away from the skylights, all of a sudden these clearances around the skylights become walkways. And so it's not just, you don't have to just think about, well, is the attachment through the roof going to cause a leak? What is much more likely, because that solar installer is making that attachment, we're assuming they're good at their job, they're doing what they should be, it's a brand new attachment. Generally what leaks is the pre-existing stuff on the roof, because a roof is not designed to be a job site. And when you get a team of workers kind of tromping around on this rooftop around existing penetrations, that can be bad for the roof. And so what we've incorporated into our design, and Half Moon, you know, what they ended up doing was actually removing the skylights, and then we put more solar panels there, and it was probably for the best that we did that. But even walking around on a shingle roof can be bad for the roof. You know, those shingles, the grit in the shingles protects the roof, and when you walk on those shingles, it gets grit off of them. So that's one reason to cover the whole roof, is that you're then shielding the shingles with your solar panels instead of leaving them exposed to sunlight. But B, what we try and do now is, instead of assembling the whole thing on the rooftop, you know, what we'll do is as much on the ground pre-assembly as possible. So we'll build our rails and mount our electronics and attachment points all onto our rails as much as we can. Depending on what lift equipment we have, we'll do it all in one piece, or into chunk it up into maybe 3 pieces, but do as much on the ground pre-assembly as possible to reduce the time spent on the roof itself. Let's see. Electricity pricing varies by season. You know, south facing gives you the most production. So we're going to talk about this in a little bit tomorrow. But there's a policy called net metering. And the way that, and we have this referenced kind of towards the end of the program, one of the last slides. But if you want to know what your net metering policy is, there's a website you can go to called desireusa.org. It's desire without the first E in it. So I'm putting it in the chat box. So you can put in your state. You know, I would click on Mississippi, but we don't have a very good net metering policy. So let me click on Iowa. And here's a list of all of Iowa's green energy policies, as well as the U.S., so you can find out information on like the U.S. tax credit and stuff like that. And I don't want to spend too much time sorting through here, but if I just type net metering, well, I guess Iowa doesn't have a net metering policy. Let me why don't we try Illinois? So not all states have net metering. It's not, the federal government does not regulate the price of electricity. It's something that's left to the states. And so here we have Illinois' net metering policy, and it applies to a variety of on-site generators up to 2 megawatts in size, and there's some limits, and net metering is a controversial policy. But it has to do with what generation is pushed onto the grid by the solar array. You know, if you're trying to offset 100% of your bill, but the solar array is only on for 1/3 of the day, then de facto 2/3 of the solar production is going to be pushed onto the grid. So how you're compensated for that 2/3 of the production becomes a controversial issue. You could view net metering as a consumer protection law that entitles the solar owner to better than default compensation. And so in Illinois' net metering policy, they say if you are on a monopoly, you're credited at retail up through 12 months. If you are on a non-monopoly, if you're on a deregulated market where you can choose your electric provider, it's credited at avoided cost at the end of the month. Now in Mississippi, we don't have a traditionally defined net metering policy. Our net metering policy is defined as no net metering, and we're credited at avoided cost, not at the end of the month, but rather instantly. So the instant we're outflowing onto the grid, we get avoided cost as compensation. Whereas in this policy for Illinois, these customers are credited at avoided cost at the end of the month. So they subtract what you put onto the grid versus what you bought back, and any surplus is credited at avoided cost. And so only a small fraction is credited at avoided cost and not the whole amount of outflow. And then if you're on a monopoly, they say, well, because you're on a monopoly, you get more rights than on a non-monopoly, and so you get credit at retail rate throughout the year until the end of the year. And this gets complicated because it's, well, what's defined as the end of the year? You know, they could define the end of the year as the end of spring or the end of fall instead of the end of December. And so even when you have a net metering policy that entitles you to outflow, there's more to the story. That's why I'm really liking doing work with batteries and off grid, because we don't have to mess with that whole debate on whether it is right for the power company to charge you 9 cents but only buy back at 3 cents, or to charge you at 12 cents but only buy back at 5 cents. You know, someone's going to be unhappy either way, whether you have net metering or not. You know, I kind of come down on, well, if you're on a monopoly, you should have net metering, and if you are not on a monopoly, then I can see why you would not have net metering. You know, where it's playing out in Houston, Texas, where they don't have any net metering laws, but they have a deregulated grid, you get better deals for your outflow onto the grid than we do in Mississippi, where we have a monopoly but no net metering at all. You know, so it's like, well, there's a clear example of deregulation benefiting the customer. So, you know, if you're going to have a monopoly, you should protect entitle your customers with more rights than what they get via open competition. But I suppose it's more nuanced than that. Now, the reason why I put it out is South is best if you get retail compensation for your outflow. But if you don't get retail compensation for your outflow, if you only get, you know, what the cost of the unrefined electricity is to the power plant, the cost of coal, the cost of the natural gas before it goes into the power plant, that's the federal minimum buyback. You know, the avoided cost of operation is what the federal government requires the power company to buy you back at. And then your net metering policy is a state policy that might entitle you to a higher compensation rate. If you don't have a net metering policy, south-facing may not be the best deal. You know, a west-facing array or an east-facing array, when you have higher loads because you're getting up in the morning and running that air conditioner, or you're getting ready for the evening and running that air conditioner, where at high noon there may be no one inside the house. And so an east-facing array or a west-facing array may produce less energy but more coincide with your load and therefore produce less outflow. So even though east or west may be producing 15% less, if the compensation for that outflow is, you know, 70% below retail, then that's not going to do you any good. And so I would caution solar designers in states that have net metering, and most states do, that net metering has changed solar design in a similar way that any subsidy impacts the unsubsidized business model. The 30% solar tax credit encourages solar installers to go for the top shelf. Because if I'm getting 30% off a Nissan or 30% off a Mercedes, I might go for the higher end product because I get that discount. Similarly, if I'm getting paid retail price for all of my outflow, I'm going to design my array around what produces the most amount of energy, regardless of whether or not it's in sync with the consumer load, for better or worse. Now, that makes net metering sound pretty bad. It might be one of the best energy policies we could actually have as a society. So, there's more nuance in that argument. But what I would say is don't just think about your solar design as having to be south facing. There's more to the equation, particularly if your outflow rate is less than your inflow rate. And for that matter, if you're doing an off-grid design, it might be that you need the most amount of energy possible, and so you're just covering the whole roof. So we made these arguments kind of earlier on in the program, but even thinking about it even more unconventionally, if I'm doing an off-grid house, my most critical power may be in the winter, and I may think, well, shoot, what if I just put the solar panels down the side of the building rather than up on the rooftop? Or if I'm in New York City and I have a bunch of electrical equipment covering the roof and I don't have any surface area on my roof, but I'm in a tall, skyscraper, the side of the building might be the collection. And so all you have to do to kind of confirm kind of crazier design ideas is just to run and do a PV watts calculation and say, okay, well, I'm producing 1.5 kilowatt hours. Let me go a little bit further north. Why don't we go into why don't we go with New York City? And so, here I am in New York City, and I'm doing a 1 kilowatt array at a 10-degree tilt angle up on a commercial flat roof facing south, and my solar array produces 1.24 kilowatt hours per watt per year. And then I think crazy, and I'm like, you know what? I'm going to go with a 90-degree tilt and run it down the side of the building, and I'm producing 938 kilowatt hours a year, which is, it's certainly less, but we're talking it's 25% less, not 70% less. So for that matter, New York City electricity pricing being over double what it is in Mississippi, if the solar arrays were installed at the same price, which I admit is a stretch for New York City compared to Mississippi, but if they were installed at the same price, a solar array going down the side of the building in New York City would be more cost effective than one installed in Mississippi. So don't be afraid of being creative with your array layouts. Let's put some numbers to these economies of scale here. South facing, if we did let's just compare doing 3 little small array sections on the south side of the building versus covering the whole roof with solar. So we would be looking at a 4.5 kilowatt array. That's a small solar array. There's a minimum amount of money that I have to make to get up onto a roof and put solar panels on it. You know, so I might charge $275 a watt for a 13 kilowatt or $450 a watt for a 4.6 kilowatt. And so if I do this small solar array at a substantially higher price, even though it produces more energy, it's going to have a longer payback than if I do the larger array at a lower price, even though it produces less energy per watt, because of the discount that I've achieved due to economies of scale. So the basic way that solar is attached to the roof is through this system of solar rail and brackets that are called L-feet. And 10 years ago, integrated L-feet with flashing did not exist. But, you know, today, the standard way to do it is to get an L-foot bracket and mount it to some flashing that slides underneath the shingle. Now, it is not a perfect process. If you are doing new construction with shingles, get the solar installer out there to put these flashings in as they're shingling the roof, because otherwise you got to get up underneath the shingle with a pry bar and pry out roofing nails. And particularly if the roofer is trying to do a good quality job and puts in a bunch of roofing nails rather than standard, it becomes a nightmare for the solar installer. There are above the shingle mounting systems that some installers are using, but you know, this flash pad, it doesn't just go back to here, it goes all the way under this next course of shingles a good distance to get that water away from the penetration. So using flashed attachments as standard on a tile roof, you get a tile to replace your tile. You know, they used to sell hooks that kind of snake underneath the tile, and that design has kind of been phased out by the industry, and they're using instead, you know, true tile replacements. There are manufacturers who kind of specialize in making the tile replacements to fit the form factor of the tile you're using. On the bottom right, we see a clip that clips to standing seam metal roofing. I actually, out of all metal roofs, standing seam metal is my least favorite to work on. We'll get into a reason why. But above the attachments, you got the flashing, you got the L-foot, and then you have your rail. And you get, regardless of manufacturer, you get clips that hook into this rail channel, and they all do it a little bit differently. And there are, you know, I am partial to certain racking companies over others, but the whole system is pretty much the same. You know, you put a bolt into this channel, and then you have mid clips that kind of space and clamp down the solar panel onto the rail between two panels, and then you have end clips that go on the very end just for one panel. And the clips have a grounding washer that grounds the panels to the rail, and then you ground the rail to your equipment ground conductor that gets run with your cables. Pro installers are going to mount to every single rafter as they go across the roof. And so the way that they do that without making Swiss cheese out of your rooftop is that they stagger the attachments. And so, you know, here's a rafter, here's a rafter, here's a rafter, and there's a 4-foot spacing between their attachments sometimes in the interior of the array where there's less wind load, that spacing can be stretched out to 6 feet instead of 4 feet. But a very good standard, you're not going to make any mistakes with this layout, is to keep your attachments 4 foot on center and then stagger them so that you're hitting every single rafter. Now, not all rafters are 24 inches on center. A 16-inch on center rafter is common as well. And so during the site evaluation, what I do is I get in there and I measure the rafter spacing, and then in AutoCAD, I locate every single attachment position to make sure that, if I have, if you have 2 rows of solar panels and you're 4 foot on center, it really doesn't matter the spacing of your rafters, because you can just, instead of going every other, you can go 1, 2, 3, 1, and then hit every rafter as you go across so that you evenly distribute the load over the truss of the roof. I like using rail that has a little bit wider of a channel, where you're using a lock nut that goes into here rather than a bolt. The reason is I like using the wide channel rail for cable management. And it keeps my cable up on my roof secured and protected, and it doesn't droop down onto the roof. And so what I do is I take my electronics and cables and I build my rail down on the ground, and I throw my cable into the top channel and secure it with tie wraps. And then when it comes time to put the panel onto the rail, the module frame itself holds the cable into the rail. You can use tie wraps. You also get cable clips, and they serve different purposes. The tie wraps can get messy. They kind of look cheap. People are concerned about them failing over the long run. The cable clips, though, the module cable can actually pull out of the clip. So it's not a perfect solution either. I kind of look at the cable clips as being a helping hand to pre-position the cable as well, but neither zip ties nor cable clips are perfect. And then once the module, what I think is perfect is when the modules get clamped onto the rail. If you have your cable inside the rail, then it's permanently secured by the edge of the module frame. There's no way that thing's ever going to come out of there. And so the sign of a good installer is able to look underneath the solar array and be able to see all the way through it. And even though we have little electrical boxes and droopy, cable whips at every single panel, the end result, you can look underneath the array and hardly see. You see the little boxes and cables right here, and that cable then is going right into this rail. So no squirrel is going to get up under there and start chewing things up as you would if you had kind of a rat's nest of cable underneath. Couple of finer tips. This is called an array skirt or squirrel guard. How good they are, I have my doubts. They do restrict airflow. You definitely would want to use them if you know you have nearby trees and squirrels on the rooftop. Otherwise, I think, using it through good racking selection, you get most of it done. These are kind of interesting. These are called snow guards. And what they're there for is to catch the snow so that it doesn't slide off the roof all at once. So in areas of heavy snow, that could be important to prevent avalanches that can rip the gutters off the side of your roof, depending on how good your gutter guy is. Purlins, if you're mounting to purlins instead of rafters, it can be a little bit trickier to get them to line up correctly. So you might have to end up going with a landscape configuration instead of a portrait configuration. You know, running the rail up the roof rather than east-west is possible, but it's not preferred. It's a more difficult install. Kind of the way the installation process works is you get up on the roof and either using like a $600 stud finder, not a $50 stud finder, but a $600 stud finder, which is still tricky. You gotta get a flat piece of cardboard and use your stud finder through the cardboard and then through the roof rather than on the textured surface of the roof. Kind of the old-fashioned way is to take a rubber mallet and bang the roof and kind of feel where the rafters are with the aid of someone inside the attic measuring it out. And so what I'll do is I'll go across the roof and I'll bang the roof and I'll take a whiteout marker and I'll just dab the roof wherever I think there's a rafter. And I'll start at the top and do it in, 3 different spots: at the top, in the middle, at the bottom, and then kind of look at my spots and see if from one row to the next, if they're lined up or not. And once you get going with it, it kind of falls into place if you know your rafter spacing. So once you've identified your rafters, you pop a chalk line to keep them straight. Drill a pilot hole. Once you drill your pilot hole, you're going to know if you hit the rafter or not. If you missed it, you can stick a wire down there, give it a twist, and see how close you are. And then hopefully you don't miss too often, but that's what the flashing is there for. So you caulk up any misses, and then, you're flashed around it. The reason why I don't like standing seam is because it becomes a weakness of the standing seam panel itself. Because instead of lag screwing into the rafter, you're now clipping onto the seam and relying on the strength of how the standing seam panel is then attached to the roof, which is nowhere near as strong as a lag screw into the rafter. And so the advice from the standing seam manufacturers is to clip to every single standing seam to get the best load distribution across the standing seam roof. Now, most installers don't want to do that because you're spending more money on your clipping system, and it means there's really no advantage of using rail, and doing a railless system is harder to install than a rail-based system. And you're not saving any money because you're buying so many more attachment points. And you're covering up the roof anyway. So, I know standing seam is kind of considered to be higher end than, rolled metal, but rolled metal is actually, better for solar because you're lag screwing into and through the roof, which kind of terrifies the homeowner. But as an installer, I can tell you that the standing seam metal roofing products, they have a industrial butyl tape that goes underneath the, you can kind of see it here, that goes underneath. And so lag screwing through that butyl tape is very well sealed, and it's a very strong attachment that you can be confident in. Now, another thing that I wish I had known on this previous project here was that there's now conduit supports for standing seam or metal roofing systems that can help you keep that conduit up off of the roof. So that's kind of nifty. I think that's worthy of note. Okay, so we are at the end of our program. Let me give the quiz a real quick run through to make sure I didn't miss any content, and then I'll pass it back to Half Moon. Because we are kind of running a little bit behind in terms of where we should be. But what we're going to do tomorrow is talk more about our wiring selection and inverter selections, and then go through some design examples moving towards our balance of system material. And then we're going to talk about some broader industry concepts. So, with that, what we're going to do is, my webcasting is making my internet a little bit slow. So we're at the end of our program today. I'm going to pass it back to Half Moon. If you have any issues with the quiz, I think it's simple enough. You should do a good job. It's kind of quick. If you don't have any issues, we'll just go over the questions first thing tomorrow. So with that, I'm going to pass it back off to Half Moon.
All right, thank you, JR. I want to remind everyone to take the quiz after the webinar ends if you need continuing education credit for this webinar. Certificates will be emailed in PDF form, and if you have any remaining questions, you can reply to any emails you have received regarding these seminars or call into our office. Thanks again, JR, for the presentation, and thank you to everyone in attendance. Here's your quiz.